First step in this practice, calculate the wavelength of a radio signal with a frequency of 100.7 megahertz. So you need to remember our equations here. We're looking for wavelength, okay? We're given frequency. We know that wavelength is equal to the speed of light over frequency. We know the speed of light, 2.998 times 10 to the 8th meters per second. Now our frequency is 100.7 megahertz. Remember, 1 hertz is a seconds to the -1. So we will have to convert this, but I'm going to do that in the calculation itself. So 100.7, there's the decimal place there, megahertz. Mega is 10 to the 6th, so it's 10 to the 6th hertz for every 1 megahertz. This cancels out my megahertz, and now this is the same as seconds to the -1, which cancels my seconds here. And I get an answer here of 2.977, my sig figs is 4, meters. So the wavelength of the radio signal with a frequency of 100.7 megahertz is 2.977 meters. Remember, that's kind of a long wavelength. That's almost, almost 3 full meters is a pretty long wavelength, but it's also a radio signal. And radio signals have long wavelengths because they're lower in energy. Okay, what is an emission spectrum and how does an emission spectrum of a gas in a discharge tube differ from white light spectrum? So remember what an emission spectrum is. Emission spectrum is I've taken some species, some combination, either a single element or a compound or something, and I've excited it. I gave it energy, which excited the electrons up to higher energy states. I then, when those electrons fall back to their ground state, they release energy in the form of a photon, h nu. Again, h being Planck's constant, and nu being the frequency. So they release energy in the form of a photon. That matches the amount of energy they had originally absorbed, because energy is quantized. It's a specific amount that can be measured. So the light is released when an electron releases that photon. And goes from the excited state to that ground state. The difference between a line spectrum and a white light spectrum, though, is that idea of a discrete spectrum versus a continuous spectrum. A line spectrum is what we observe with those gas discharge lamps. They're discrete lines of color that represent the photons of those specific wavelengths. It's like a fingerprint or a blueprint for that species that we're interested in. But again, when you look at a gas discharge tube for a light, you may see, you know, whatever colors they may be. I only have so many colors available right now. But you're going to see very specific colors of wavelength. So green is over here comparative to the blue. But you're going to see very specific wavelengths of color show up unique to that compound. Now, if you have a continuous spectrum is like white light. And so a white light spectrum is called a continuous spectrum. It looks like a rainbow. And that, in fact, that's why rainbows look like they do, because you're seeing white light or sunlight pass through a prism in the sky, and you're seeing a continuous spectrum. There's no discrete lines, there's no breaks of the color. They're blending from one color to the next. And white light does that because white light is exhibiting all colors of the rainbow at you at one time. What's next? Which of the visible colors of light has the highest frequency, and what does this mean about its wavelength? Well, let's think about the colors. Visible colors are your rainbow, right? So your highest frequency is also your highest energy, and that is your purple. I don't have a purple color out on my markers right now. What does this mean about the wavelength? Well, highest frequency equals highest energy. Now I'm going to change this from saying highest to higher because this is only highest within the visible spectrum. It's not the whole electromagnetic spectrum. Okay. Just within the color spectrum itself, the visible spectrum, it's the highest. But the higher the frequency, the higher the energy, the shorter the wavelength. So again, it's really asking about this to this. I'm just including the energy in there just so that we remember that and are on the same page. Next up, calculate the wavelength of each frequency of electromagnetic radiation. Okay. Again, I know lambda is equal to my speed of light over my frequency. So I want the wavelength. I know my speed of light is not Planck's constant. Speed of light is 2.998, 10 to the 8th meters per second. My frequency here is 100.2 hertz. Remember, 1 hertz is 1 second to the minus 1. So this is literally the same. I could rewrite this as, a seconds to the minus 1. So my seconds here are going to cancel out. Give me my meters, which is what I want. I calculate this out and I get 2.992 10 to the 6th meters. If I have 1070 kilohertz, lambda here, 2.998 10 to the 8 meters per second, my speed of light, divided by 1070 kilohertz. But I need that in hertz. I know that 1000 hertz equals 1 kilohertz because kilo just means times 10 to the third. So my kilohertz have canceled. My hertz cancels my seconds here because again, I know 1 hertz is 1 second to the minus 1. I calculate that out and I get 280. I need 3 sig figs here because there's 3 sig figs here. That 0 is not significant. There's no decimal place there. 280 decimal place here to emphasize this 0 is significant meters. What's up next? The emission spectrum of sodium consists of 2 closely spaced yellow lines around 589 nanometers. What is the frequency of the light? What is the energy of 1 photon of light with a wavelength of 589 nanometers? And what is the energy of this light in kilojoules per mole? Let's figure it out. First up, my frequency. I know lambda is equal to the speed of light over nu. So I'm just going to rearrange this. That means nu is equal to the speed of light over lambda. So speed of light over lambda, speed of light, 2.998 times 10 to the 8th meters per second. Lambda is 589 nanometers. Now I do have to convert that nanometers to meters. 589 nanometers 1 meter is 10 to the ninth nanometers. Remember, 9 and nano go together. This gives me an answer here of 5.09, 10 to the minus 14, seconds to the minus 1. Or you could write hertz there if you really wanted to. I just write seconds to minus 1 because I'm going to be using it in a future calculation. So I'm going to move this. I may have to delete this in a minute. We're going to see on space. Going to move this up here. So again, that was A. Looking at B, what is the energy of 1 photon of light with a wavelength of 589 nanometers? Okay, I know energy is equal to hc over lambda. I know h is Planck's constant, 6.626, 10 to the minus 34th joule seconds. I know my speed of light is 2.998, 10 to the 8th meters per second. And again, I have 589 nanometers here, but I need that in meters. So I'm going to convert that. I know 1 meter is 10 to the ninth nanometers. This gives me 3.37, 10 to the negative 19 joules. And then it asks, what is the energy of 589 nanometers of light in the units of kilojoules per mole? So let's just convert that. I know I have 3.37, 10 to the negative 19 joules of energy of 1 photon of light with a wavelength of 589 nanometers. So I'm going to convert that to units of kilojoules per mole. I know that I have 6.022 times 10 to the 23rd photons in every 1 mole of photons. Again, this is 1 photon. I'm just scaling it up. And 1 kilojoule for every 1,000 joules, I get 203 kilojoules per mole. 3 sig figs throughout because that wavelength was 589 nanometers, and Planck's constant has 4 sig figs, and speed of light has 4, so I'm good there. Next up, consider the portions of the electromagnetic spectrum. We've got microwave radiation, X-rays, green light, and orange light. Rank these in order of increasing wavelength, increasing frequency, and decreasing energy. Well, increasing wavelength is going from higher energy to lower energy. So my highest energy here is X-rays. Next in energy is my green light. Next is orange. And again, I know it's asking for wavelength, but I think about it in terms of energy. My longest wavelength will be microwave of this list. Increasing frequency. Frequency and wavelength are inversely proportional to each other. Remember, lambda equals c over nu. Remember, E equals hc over lambda. They are inversely proportional to each other. So when I want to do increasing frequency, microwaves are the lowest. Next up, microwaves are less than my orange light, less than my green light, less than my X-rays. And decreasing frequency, X-rays are the highest, Green light is next in line, followed by orange light, followed by microwaves. What is the wavelength of visible light? Visible light is roughly 400 nanometers to 750 nanometers. You will hear some people say 800 nanometers here, but that's getting on the outskirts of what visible light is for us. Okay, the last problem in this module you may or may not be able to do depending on when you learn your thermochemistry. So this problem may be fair game now, maybe fair game later on this semester. But it is pulling together a couple different concepts, and you should be able to do at least part of it now and all of it by the end of the semester. A microwave oven heats by radiating food with microwave radiation, which is absorbed by the food and converted to heat. Okay. Suppose an oven's radiation wavelength is 12.5 centimeter. A container with 0.250 liters of water was placed in the oven, and the temperature of the water rose from 20 degrees to 100 degrees. How many photons of this microwave radiation were required? Assume all of the energy from the radiation was used to raise the temperature of water. So first up, let's think about the energy here. E equals hc over lambda. Planck's constant, 6.626, 10 to the minus 34 joule seconds. Speed of light, 2.998, 10 to the 8 meters per second. My wavelength here is 12.5 centimeters, which I do need to convert to meters. That is the same as 0.125 meters. This gives me a numerical value here, 1.59, 10 to the minus 24 joules. Now I have the amount of energy required that went through at that wavelength. Now, I need to move the page up for a little bit. So I will move that back down when we need it in a sec, but I can't write that low on my screen. To do the change in temperature here, we're going to use our MCAT equation from our thermochemistry chapter. So Q equals MCAT, where Q is the heat, M is mass, C is specific heat, and delta T is change in temperature. My mass here, I need the mass of the water. I have 0.250 liters of water, and unless otherwise told, we are going to assume the density of water is 1.00 grams per 1 mil. We know that there is 1,000 milliliters in every 1 liter. Therefore, we have 250 grams of water here. My Q is equal to my 250 grams of water times my specific heat of water, which is 4.184 joules per gram degree C, times my temperature change. Final temperature, 100 degrees C, minus initial temperature, 20 degrees C. This gives me a heat Q value here with 3 sig figs, 83,700 joules of heat. So this is the amount of heat I needed to heat up that water. Sorry, I'm trying to find the right button. This amount of heat needed to heat up the water. This is the amount of heat, or this is the amount of energy at that wavelength. So my number of photons is going to be the difference between these two. I will move that down in a sec after I write this down. But my number of photons here, (83,700 joules, 1.59, 10 to the negative 24th joules, gives me 5.27, 10 to the 28th photons needed or required, whatever you want to say, required to complete this temperature change. It's a lot